In this video, we're going to look at exponential decay. So by the end of the lesson, you'll be able to graph functions displaying exponential decay, and we'll also talk about transformations from parent functions again, and also apply exponential functions to real data. So again, the essential questions that you're thinking about through the lesson: how do exponential functions model real-world problems and their solutions? And we will look at another example of one of those. And how can I describe transformations from a parent exponential function? And so the new vocabulary in this lesson will be exponential decay and decay factor. Just like we did with growth, we're going to start by just modeling what one of these looks like. So as a quick recap, an exponential function involves the expression some base to an x power. The base is positive and it's a number other than 1. Exponential decay functions are a little bit special. We were before looking at base values greater than 1. Exponential decay has a base value between 0 and 1. So for example, if we look at this function 1/2 to the x power, we'll start by putting in some values for. So with this one, we'll also start with choosing some values for x. So we'll start with -3 and go up. And if I were to plug that x into f of x is equal to 1/2 raised to the x power, for a -3, I would get 8. And for -2, I would get 4 and 2. Anything to the 0 power is 1. And then 1/2 and 1/4. So you might have noticed this is the opposite of the pattern that we were looking at with exponential growth, but we're going to plot these points just like we did in that first example. So the first one that I want to plot is -3, 8, and then -4, 2, -1, 2, 0 and 1, 1 and 1/2, and 2 and 1/4. So if we want to describe the end behavior of this graph, we would say as x approaches positive infinity, on this graph f of x approaches 0. And as x approaches negative infinity, f of x approaches positive infinity. And that first example of f of x approaching 0 is our asymptote for this graph. And so again, that's when you move away from the origin and the line or the graph approaches a line. And in this case, that line is y equals 0, or the x-axis. So next we're going to look at some transformations of these exponential decay functions with a, h, and k. So in this first example, we have -3 times 1/2 raised to the x plus 2 power plus 1. And let's go through and label. -3 is our a value, this 2 is our h, and 1 is our k. The first thing that we want to do is graph the parent function, which is -3 times 1/2 raised to the x power. Now, from this, that a value is going to be our y-intercept. So I know that the first point that I can plot would be 0, -3. And then if I just plug 1 into this function as the power of x, I would get out -3/2. So another point that I could plot would be 1 for x, -3/2 as the y value. And I know that this will approach an asymptote of y equals 0, and we'll continue to curve down toward negative infinity. And just double check that, but because our a value is negative, it's inverted about the x-axis. And then the next thing that I want to do is translate this graph. So because my h is a positive 2, I'm going to move that entire graph 2 units to the left. And because my k value is a positive 1, I also need to move that entire graph 1 unit up. which means that this point, which was at 0, comma, negative 3, is moving over 2 and up 1. And this point, which was at 1, comma, negative 3 halves, will move over to negative 1 and negative 1 half. And it should curve down. So the red line is actually the function that we wanted to plot, which is negative 3 times 1 half to the x plus 2 power plus 1. And the one thing that you really need to check is to make sure you shifted the entire line up. So that asymptote, which was at y is equal to 0, should now be up 1 to y is equal to positive 1. Remember that the k value is what your vertical asymptote will be. Now, domain and range of this one, just like with exponential growth, the domain is going to be all real numbers every time. And in this particular example, our range is equal to anything where y is greater than 1. Or, sorry, everything where y is less than 1. We also want to look at an exponential decay model using real data. So just like with exponential growth, we're talking about when a quantity is changing by a fixed percent over a given time period, usually in years. And this time, it's a fixed decrease every single year. And so the formula that we're using is y, or our adjusted amount, is equal to a, the initial amount, times 1 minus r. Remember, r is that percent decrease now, expressed as a decimal. Do not forget to change it to a decimal. And then t is the time. And then 1 minus r, that quantity in parentheses, we call that the decay factor. And then the r itself is the percent decrease. An example to remember is when you buy a new car, you lose a certain amount when you drive off the lot, but after that it tends to depreciate or go down in value every single year. So here we're looking at an example that we started out with it worth $12,000, and it's going to depreciate at an annual rate of 15%. So we want to use, again, this kind of generic general formula to create one specific to this problem. So in this example, A is going to be $12,000, the initial start value. 1 minus R, we're talking about an annual decrease of 15%. So I want to write that as a decimal, so 15/100th, and to any time t power. And I want to simplify that to 12,000 times 85/100th raised to the t power. So the two questions I want to answer here are, how much will the scooter be worth after 4 years? And then we want to estimate when the scooter will be worth $2,000. When we go into logarithms, we'll be able to calculate specifically how much or when it would be worth $2,000, but right now we're going to practice graphing so we can make an estimate. So the first question, how much would it be worth after 4 years? All I need to do here is plug 4 into t. So my time t is going to be 4 years after we purchased it. So y is equal to 12,000 times 85/100th raised to the 4th power. And when I do that math, I get $6,264.08. So after 4 years, that will be the value. When you're doing these estimation graphs, a good strategy would be to read the entire problem and see what you're actually looking for so that you know the best place to start guessing. Otherwise, you're just randomly picking numbers. So my x-axis is going to be the number of years after the purchase. So years after purchase. And I will start out with 0. And just go by ones. And our starting value was 12,000. And again, we're just going to go by 1,000 each time. 8, 6,000, 4,000, 2,000, and 0. So when we bought it, it was worth $12,000. And after 4 years, it was worth 6,264. So there's my 6,000, so right about there. I'm just going to pick 10 to try as my next value. So if I plug 10 in for t and I use that same equation, I'm going to get $2,362 out. And so for 10 years, I will find 2,000, and it would be right about there. Now that actually is pretty close, so that's going to probably be my answer. But let's go ahead and try 12 years. If I put 12 years into that same equation, I get $1,706.90. So that's 12 years. And 10 years was $2,362. So a reasonable estimate here might be about 11 years. If I actually plugged in 11, I would get $2,008 out of that function, which is pretty close. So 11 years is a perfectly reasonable estimate, and soon we will learn again how to calculate exactly when it would be worth $2,000. The last thing for this lesson is several practice problems. So please complete these and come prepared to share your answer in class. So the first 3, tell whether the function represents exponential growth or exponential decay, and definitely be ready to explain why. 10 and 11, those 2 examples here, go ahead and graph the function. It doesn't have to be perfect, and please do not use a graphing calculator. Do this by hand. And then 10 and 11, state the domain and the range of the function. You do not have to graph this in order to do that, but if you find that you're needing some extra practice with the graphing, please go ahead and do that as well.